Right, so you guys have already done a course on probability and random processes or probability and stochastic processes. In your second year, right? So basically, you know what is randomness and how do we assign probabilities to random events. 1, 2, what are random variables and how do we let their actions such as expectation, correlation, and and fine. So all of this would have been covered in some detail or maybe due to the online mode in less detail. So what we'll do is we will quickly recap all of this. Quickly and then to the topics specific course. Fine. So in doing that or in the quick recap, let us so one is something called random. So before I launch on a or latch on to a more formal definition of randomness, I'll ask you, when is something called random?
Like when something is not predictable.
When something is not predictable, right? So who said this? Sorry.
Navya.
Oh, Navya, hi. Yeah. So when something is not predictable, and based on this, we will define a random experiment as an experiment whose outcome cannot be predicted before the is performed. Right? Examples. I'll give you the same examples from your previous course. The tossing of a coin, the rolling of a die, the drawing of a card from a pack of from a shuffled pack of cards. All of these are simple random experiments or random experiments that we are rather comfortable with. And so a random experiment. See, my hand hitting this lower bar is a random experiment, and the color of the pen is the outcome of that random experiment. The random or a random experiment, and therefore has multiple possible outcomes whose hoods are are yeah whose likelihoods multiple possible outcomes, each of which has a certain likelihood right. There are multiple possible outcomes, each of which has a certain likelihood of happening, and the collection of all the possible outcomes. Uh, what happened? The collection of all the possible outcomes of a random experiment is called what? The collection of all the possible outcomes of a random experiment is called what?
Sample space.
Sample space. Yes. The sample space. Fine. And for the rest of this course, denote sample space by omega. Fine. Whenever we talk of a sample space, we'll denote it by omega, and the possible outcomes omega of a random experiment are elements of omega. Fine. So if and has the outcomes omega 1, omega 2, n, then elements of omega, an outcome is the most basic result. So when we say that an outcome is the most basic result, means there can be other more complicated results. These are called events. Event is the set of one or more outcomes of a, not an, random. For example, when we roll a die, and say that the out or the result then the possible outcome are contained set E. Fine.
Yes, sir.
So
Sir,
yeah,
even can also have 0.
Bala,
What?
does the die have 0?
I'm saying that even is a set of one or more. You write in definition.
What is omega in this case, Bala?
I'm saying about definitions are not example.
So when you are the outcome of a die, when you say that
I'm not saying about example, sir.
yeah, then
Definition.
definition.
Event
So
is set of one or more, but it can also be 0 of collection of outcomes.
yes, that is a set of outcomes. My bad. Set of outcomes. Fine. I'll formally define it later. I haven't formally defined it till now, but yes, you are right. So an event is a set of in that case. Okay, Bala?
Okay, sir.
Yeah, great. Thank you. Yes, so yeah, you're right. But that null set thing skipped my mind for a moment. Thank you. So for the coin, and as Bala pointed out, the possible events are so the coin gives an outcome and the impossible event that nothing happens. So these are the four possible events from the toss of a coin. And the formal definition of an event, oops, formally an event.
Excuse me, sir.
Yeah, Siddharth.
Sir, I'm not able to see your screen, sir. Actually.
Okay, Siddharth, hold on a second. Let me write whatever I'm writing. Then I'll is subset of the space. So Bala, this is the formal definition. The other one was just to introduce the idea of event, but yeah, you are right. We should be careful with the informal ones as well. So Po here cannot see my screen, so I'll just yeah. Formally, an event is a subset of the sample space, and for which T defined. This is the formal definition. And for so sample spaces come in two flavors. What are those? What are the two types of sample spaces? Discrete and continuous. So rolling of a die, tossing of a coin, picking a card from a deck of cards are all discrete sample spaces. Continuous sample spaces would be the temperature at any given instant, my ever increasing weight, the okay, my yeah, those are random variables, or the no, not the number of dust particles in my room. Yeah, the temperature, the any number cannot be a continuous sample space. So the temperature, basically the any the xy coordinates of the coin that you threw for conducting a discrete sample space head tail experiment. All of those are examples of a continuous sample space, and discrete sample spaces can be finite or countably infinite. But continuous sample or non-discrete sample spaces are fine. Countability, I believe you know, so I'll not go into the details of that. And for any set omega, the sigma field of omega is a collection of all the subsets of omega. Fine. So what I know that this is defined only for discrete sets. This is defined for both discrete sets, but the sigma field of a discrete set is same as its power set. Fine. And since events are subsets of the sample space, we define an event as and the context of theory, the sigma field B the sigma field B of the sample space omega is also called the event space such that for all I think I should make omega boldface as well. Omega is boldface. E is also boldface. E is a set. Or let's do away with this boldface business, because otherwise we'll have to change pens too often, and the software isn't too amenable for that right now. Fine. Now the event space be defined over the sample space omega has the following one as a subset of B. 2, if E is an element of B, then is also an element of B. How can you prove this? E complement, let me define, is, or E complement is this need not be proven explicitly. 3, even then union I equal to 1 to n, EI is also an element of P. Having defined the event space, now define the measure B as a value set this Also, for all or rather as a real valued set function that assigns the values or the elements of B values between 0 and 1. Now we can write 1. This PR is a real valued set function. So it takes a set as an input and gives a real number between 0 and 1 as an output. So this is the empty set. Fine. And any triad omega B PR that satisfies called is called a probability space. Fine. So any questions with this? So any questions with this definition of the probability space, Bala?
No, sir.
Okay, okay, great. So since we have defined a probability space, now,
Sir, hello.
yeah. Who is this?
There should be probability of union of EI in property 4.
Oh yeah, probability. Yes, thank you. Typo. Thank you. Limit n tends to infinity. Yes, thank you, Chandra. I means yes, this is something that happens while when you write while you are talking. I didn't notice this. This should be probability. Yes. Yeah. So that said, now the question that I would want to ask is that okay, let me paste a picture again. Okay, why paste a picture? I'll draw it. So let's see if I can draw a shape. Paste grid. Okay. Library. Okay, I can always post a post-it note here. Just that cannot make that note circular and make this larger. See, I rotate it. And now suppose that it's easy to draw a circle here. Okay, this looks like my face anyway. So okay. I'll delete this. Try it again. Delete. So this is the post-it note. So let me enlarge it slightly more. So now say suppose I drop my pen at random on top of this yellow space. Say this. Oh, this outcome was totally unexpected. See, it's not registering. But you see that I can say if this works properly, then when I drop the pen at random over this, then the point will have certain x coordinates and y coordinates. Say this is the x-axis. Intentionally, this is the y-axis. X, y. So each of these points can be described in terms of its x and y coordinates, right? But and this node, this yellow surface, this is a sample space. This is a continuous sample space. So this is a continuous sample space. Hold on. So yeah, since this is a continuous sample space, then an outcome will basically be the pen landing at any point. So the pen having will have finally an x and y coordinate. So can I define an event as the pen landing precisely at rather. So can I say that the an event is that the pen lands precisely at these points? Chandra, can I say that? The pen is landing precisely at these two real numbers. So this is one possible outcome. Navya?
Yes, sir. It's one of the possible outcomes.
It is a possible outcomes, but can I call it an event? So can I say that beforehand the pen will land precisely at 1.0000000 and E? E, you know, is I cannot speak it out. It's 2.7 something.
It can be an event, but
Yeah,
the probability again varies.
yeah, the probability will be close to 0. That will show. So, but we won't actually have enough resources to even describe the precision of that event. So in case of continuous sample spaces of continuous sample spaces, we define events as continuous subsets of, not continuous subsets, means define events as ranges. I'll define these more formally in a minute. Ranges of the sample space. That is, instead of saying that it falls precisely at 1 and E, which in which case I'll have a large probability of going wrong. What I'll say is, or a large possibility of, it'll fall somewhere between minus, sorry, 0.99 and 1.01 and 2.7 and 2.75.
Sir, but the other one is also event, right?
Yeah, that's also an event. That's called a singleton event. We'll come to that. We'll show that those have probabilities equal to 0. We'll show that in a while. If not in a while, then possibly. So Friday, Friday there are no classes, right?
No, sir.
Right?
It's
Why, sir?
holiday.
Sorry,
Yes, sir. Friday is a holiday.
and Friday is not a holiday. Friday is technique, but so Friday there are no classes. So if you guys want, we can have an extra class on Friday.
No, sir.
Sir, please no.
Okay.
Okay.
Yeah. Okay. Fine. No extra class on Friday. No post on Sundays. Yeah. So this, yeah. So these are ranges in the and events. In this cases, in this case are more conveniently defined as countable unions of semi-closed subsets of the sample space. That is, for an or a continuous sample space omega, I define the event E as union of I equal to 1. I equal to 1 to n I semi-closed intervals, and these are subsets of omega. Fine. And the event space in this case is defined as the collection of all the subsets of omega that satisfy the above. The probability measure, here it is. The ability measure in this case for an event E is defined as probability of E equals E f omega d omega, where f omega is called the this is grossly misbehaving, but yes, one note misbehaves more, so I'll excuse this. The density is called the probability density function, which we'll redefine. Again, if E is a subset of F, crashy today. Again, if E is a subset of F, then probability of E is less than or equal to probability of F if E then probability of E equals A to B minus F omega d omega. Let plus delta minus, sorry, A plus delta, not A plus delta minus. Then probability of E equals A to A plus delta minus omega. Okay, so I have entered the battery saver mode. And if delta tends to 0, then E tends to set so equals FA times delta, or rather I should write limit delta tends to 0 FA times delta, which equals 0. So the probability of a singleton event happening is 0. So Navya, those are events, singleton events are events, but their associated probability is 0. This,
Like, is it exactly equal to 0, sir?
yes, this is for
There will be
continue.
possibility, right?
No. So if you take a graduate course on probability, there's an even more rigorous proof for this. Since this is not a course on probability, rather this is a course on communications. This is all what we'll prove here. But yes, this is exactly 0. These singleton sets, singleton elements are called zero measure sets, or singleton subsets of the sample space are specifically called zero measure subsets or zero measure events for this very purpose, that they do not have a probability measure. We'll go on to prove something even more fun using this. So now, example. We'll stop after this example. Example. Let omega equal to R and E equal to Z. Fine. So let omega be R and E be the event of E be the set of integers. Fine. So we can write E as union of I union of I equals 1 to infinity I union minus I union 0. I can do this. But probability of so this makes sense, or is it mathematically correct? I'll make sense out of it possibly in the next class. Is this mathematically correct?
I think so.
Yeah, so the probability that you choose an integer, so if you choose a real number at random and you choose an integer out of truly at random, not you don't deploy a human for that. If you deploy a human, that would limit the, or humans cannot perceive the real line. That is one thing. So we can only perceive discrete spaces for that matter. Anyway, so if you deploy a human, this will be wrong. But if you have the real line, then and have a random true random number generator, then the probability of generating an integer is 0. Or for that matter, the probability of generating outputs from any countable set over an uncountable sample space is 0. Fine. So we'll continue next Monday and stop here. So this Thursday, I'll be discussing questions about AM and FM. We'll discuss questions related to probability and whatever we cover in the next tutorial. Fine. Okay then. Bye all of you. Have a nice day.
Have a nice day, sir.
Bye, sir.
Bye.
Thank you, sir.
Bye, sir.